So hello, I'm Stefanos Kaxiras. So this is again joint work with a bunch of people at Uppsala, including Kostis Agonas, Alberto Ros, who are here, and the people who actually did all the work. So is David Klaftenegger, Magnus Norgren, and Chris Sakalis, our great students who are programming this. Okay, so you see there the title is a little bit changed from what is in the program, but I think it reflects better the abstract. So this is about distributed shared memory. Okay, so this is work that it started some time ago. It was inspired by our coherence work that we did in Uppsala for hardware cache coherence, and at some point we ended up implementing this in software. And if you think about it, why do we want to look at that again, right? So we are in an era where big memory matters, right? So we want to run programs with huge amounts of memory, big data workloads, and so on. So what I'm going to try to do here today is present a case for the distributed shared memory. Okay, let me start with a quote. So distributed shared memory is one of those holy grails for simplifying parallel programming, but sadly these systems have never been shown to scale well. So this is actually from one of our reviewers in our first paper, the HPDC 2015 paper, where we presented this, and it's actually right. So why try this again and why try it now, right? So the reason why we want to look at the DSM is that it gives us transparent caching, so it takes away, it takes advantage of locality, and even if locality is very little, still it's a function of how much you pay in latency, right? So oops, sorry. Okay, so even if it's tiny locality, it's a matter of, it's a function of latency. So even if you have little, you will benefit from that. It frees you from having to distribute the data around the system, so it gives you demand fetching, it gives you prefetching, and can largely hide bad distribution of your data because it can reorder them. And it provides natural and familiar synchronization constructs, so locks and shared memory, so we all know how to do that, and avoids the problem of having to deal with two separate systems, two separate models, shared memory programming in one node, and then message passing across the nodes. Okay, but it has been proven costly to implement in software, so you have to implement coherence, synchronization, all these things. So a lot of people say just do RDMA instead, right? Just go and read whatever you want. But this doesn't really help you because it doesn't provide any of the above. Okay? So the reason why we want to reconsider is if we look at the trends, this is CPU speed in megahertz. I'm sorry, but this doesn't really work for me. Well, it annoys me a little bit. Okay, so if we look at CPU in speed, okay, you will see here over the years, 92 to 2001, I'm plotting here. Obviously, here's the power wall, right, where we stop scaling the frequency of the CPU. This is the trend for memory latency in nanoseconds. This is bandwidth in megabits per second, and this is network latency in nanosecond. Okay, so the network is actually advancing pretty well, and you see these trends. These trends actually continue for newer and newer networks, TrueScale, OmniPath, and beyond. But it's interesting if you translate this graph, if you normalize everything to CPU cycles. So the thing that changes here considerably is bandwidth, network bandwidth, which is now measured in how many cycles do we need to transfer 1 kilobyte of data. Okay? So the first DSMs appeared here in early 90s, and at that point in time, the network's latency was huge, right? So you could do things like send a message across and then have some code on the other side, some message handlers to do the coherence, to do whatever for you, right? You could afford to do this. And that's not true anymore. So if you want to do something today, you better not have anything running on the other side. Okay? So message handlers are not okay for today. They were in the first DSMs. Now, network bandwidth is very interesting because, as you see, this metric was increasing, which means that it was getting worse, right? So there was a time where networks were getting faster, but processors were getting even faster, okay? So network speed was improving more than network bandwidth, and that was a counter-incentive to do distributed shared memory, up until the time where we had the slowdown of the processors. And now, network bandwidth is an incentive to build distributed shared memory, because it increases quite a bit. Okay, so back then it wasn't important to optimize. It was very important to optimize for bandwidth. Today, what we can do is we can trade bandwidth for latency. Okay? Now, and if you think about it, the DSM, the way we did it before, it was very, very costly because of somehow we were doing it wrong, right? So we had centralized coherence for distributed data. So if you wanted to write something, we had directories. So you had to go to a home node, figure out where all the other copies are, invalidate these copies, get acknowledgements, and proceed with that. If you want to read something, again, you had to go to another node, to a home node, where the directory is, find out the latest value, get the data, and so on. Okay? So we had many copies distributed, and we had to go to centralized locations to handle the coherence for those. For critical sections, also, we were doing it wrong because critical sections is inherently serial execution. If you run critical sections, it's one after the other, right? It's serial execution. Yet, we were allowing critical sections to run all over the system, which means that data were hopping all around the system. We had migratory data going all over the system. And this data, again, where the control for this data was centralized somewhere else. Okay, so that was very, very inefficient. Instead, what we want to do is we want to do distributed coherence. So all decisions, all coherence decisions, we want to make them without talking to anybody. Okay, and for this, we have self-downgrade and self-invalidation. And also, we want to have centralized critical section execution. We want to run the critical sections in one place, one after the other, no coherence, no overheads. Right? And for this, we have queue delegation locking, where we delegate critical sections to the lock holder. Okay? As you may notice, these things, self-downgrade and self-invalidation, tend to consume lots of bandwidth, but it's exactly the trade-off that we want to do. We want to trade bandwidth for latency. And we can implement such an invalidation, such a coherence protocol without any message handlers. Okay, so let me just give you an idea of how these things work very roughly. So if you want to write something, right, you do a self-downgrade on release synchronization points. So for example, unlock, signal, barriers. So if you want to write something, you do a self-downgrade, and you write to the home node, you expose the new values to the home node of that. So there's no invalidation on writes. You don't have to invalidate any other in the system. Okay? Now, how can we make this efficient? We can make this very efficient by implementing a software write buffer, where we put all our writes in there, and we slowly paste them to the memory system, right? So we propagate the writes to the home nodes, and at synchronization points, the only thing we need to do is just empty what's left in this write buffer. So the latency in synchronization points is limited. For reading, we have self-validation on acquire semantics. So if you have acquire synchronization, locks, waits, barriers, etc., if you have a cast copy, say here, and you want to read it, you do a self-invalidation. You get rid of the old values, and then you will find you will go and get the new value from the home node. Now, the reason why this is really important is that there's no indirection to find a new value. You don't have to go to the home node and then to the one that has the latest value. You find it directly there at the home node, and that's very fast, and again, without any message handling in these two forward requests. Okay? So, self-invalidation and self-downgrade means that all of this is based on synchronization. And in fact, the model for this is that we have sequential consistency for data race-free programs. I will relax this in a moment, but essentially it's the synchronization that drives coherence in the system. And since we allow a very weak consistency model, there's ample reordering of memory operations here, and this is where you get a lot of benefit for performance. Now, let's move to critical section execution. The trouble with critical section is that they're inherently serial, of course, right? And if we execute them anywhere, then we're just migrating the data all around the system. Okay? Now, worse, if we implement coherence the way I described, what you have to do here is that for every unlock, you have to self-downgrade the data, expose your writes, and every lock, you need to self-invalidate your caches, right? Which is, of course, this will wreak havoc on your local caches here. So we depend on queue delegation locking, which was presented in 2 papers earlier. And the idea here is that you delegate critical section execution to the current holder of the lock. So if someone here in this node gets the lock, then you delegate all your critical sections locally, and you only have to do one self-invalidation and one self-downgrade, no matter how critical sections you run there. And then there's no latency between CS, critical sections. There's no synchronization, right? All data are local to the node. There's no migration of critical data across nodes. And of course, only when you hand off the lock to another node, then you need to do self-invalidation, self-downgrade. And then on the other node, again, you will delegate all your critical sections to the lock holder, and it will run a big bunch of them with only synchronization at the endpoints. Okay. Now, one very interesting feature of this, of the queue delegation locks, is that you can detach the critical section and you can continue executing. So you can delegate and forget. Or if you want something from the critical section, you delegate, you keep going, you execute, but then you have to synchronize later. So this is something like future. And you can use selective self-invalidation and self-downgrade here, so you don't have to empty everything from your cache, but just what the critical section needs. So if you want to do that, you can self-downgrade what's needed to run the critical section. Here's a critical section. And you can delegate this across to another node, okay? And you can continue executing here. And on the other node, you self-invalidate, selective self-invalidation for only what you need in here, so you can read the new values. You execute the critical section, and you expose the results. Now, if later you want to use the results of this critical section, you do a self-invalidation, and suddenly you see these results on your node. Okay? So you can delegate and continue executing, and then catch up with your critical section much, much later. Now, this is important because it allows us to send code where the data are. Okay? So we can, instead of moving the data around in the system, we can send a pointer to another node and say, execute this for me, please, and I'll sync with you later. Okay. So we have ArgoDSM. We're using all of this. We built ArgoDSM. It's a user space implementation. It's space-based, uses virtual memory, faults for misses. Pages have a home node. For now, we just have a very naive distribution we use the MPI as the network layer. So there's a lot of inefficiency there, but it's OK for our first implementations. And we can run pthreads. Just take your pthreads programs, if they are data race free, and just compile them and link them with our library, and they become an MPI program that run across the cluster. Okay, so under the hood we have self-invalidation and self-downgrade, queue delegation locking, weak consistency, and soon we will be able to offer TSO consistency. We had a paper with Alberto Rossi in Micro 2016, where we describe how you can get to a stronger consistency model by still doing only self-invalidation and self-downgrade. Okay, so we run this, we use this to run our experiments. These are some scientific HPC codes, some typical HPC programs that you see run as benchmarks. And what I'm showing here is speed up and number of threads. So our university cluster, the times we could get allow us to go up to 2,000 threads. And just by looking at these speedups, they look fairly decent. You see here values like 600 and 200 and 400. Not this one, but that's OK. Just to give you an idea, so this is the scaling. I just zoomed in one of the nodes. So this is the scaling you see in one of the nodes. The pthreads program is the green line, and then Argo takes over and expands it outside in the cluster. Okay, so our first results looked very, very promising. These are just pthreads programs that are scaled, the original program scaled across nodes. But we're still in the HPC mode. I haven't talked about big data yet. So we started from a model where we had cores and private caches, L1 caches, and memory. And this is where we developed our coherence work. And then we moved into a distributed memory approach, right? And the distributed memory, the cluster approach, where you have increased latency here. OK, so this is still the HPC mode, where essentially we have one-to-one correspondence of cores and memory. You run your program, you use all cores, you use all memory. Okay? Big data, however, might not be exactly this model. So how would this tie for data center and cloud workloads? And in many cases, we see that there's only the need in these big memory workloads to use one node, but very big memory. Okay? So it might be that you run an in-memory database, and you don't have enough memory in one node. You might be running graph workloads, and you just need huge memory, but you don't want to allocate millions of threads around your system. So it might be one or more nodes executing, essentially, but many more nodes providing memory. Okay? We call this the big memory mode, where we decouple the allocation of cores to the allocation of memory nodes. Right, so now Argo Big Memory is a user space program spilling over to all the memory of your cluster. And right now we can run unmodified Python programs. You get your Python program, you ask as much memory as you want, and you get it from your cluster nodes. And this is a scale up in terms of memory in a scale out setup. OK, so what can you do with this? One other model, as I showed here, here you have part of the global memory in your node. You can make this entirely a cache node, right? And then try to maximize locality if it exists in your system. So all the external nodes are memory, and all your local memory is just a huge cache. Another thing you can do is there are cores here that are not used, or they're used for something else. And of course, what you could do is you can run little things here without using all the core capacity of your cluster. But you can run helper threads here, helper programs, to help your case, right? So for example, Alexandra talked about decoupled access execute. You can run access phases remotely and know what you think you are accessing, so you can potentially be prefetching or presending remote memory to your cache, okay? Or you can do some near data processing where you run some helper threads to pre-process your data, okay? These are all becoming extremely active areas in research, and people are looking how to do this, and we have a platform where you can actually experiment with all these approaches. So big memory mode, this is just data produced last night, very recent. What I'm showing here is we have a Python-based spectral filter application for meteorology. The meteorology department has this program. They asked if they could run in big memory. We said, sure, just link with our library, and it runs. Okay, so these are just runs, simple runs without any optimization on top. The red and green, the yellow line are Argo. The blue line is swap space, and this dotted line here is what would happen if you had local memory, which you don't. It doesn't. This line doesn't really exist, just a projection, right? And this is the number of iterations as the program progresses, what happens, how much time it takes. So as the program is running, swap space becomes slower and slower. It's about 8 times the slowdown if you had everything in local memory. Argo is 3 to 4x slowdown, so it's much faster than swap. And this is not a very big workload, right? We use bigger workloads. The results are really impressive. Swap goes extremely high up. Argo is still there. Our goal would be to lower these two lines to close to the green line, so we can run big memory programs at native speeds, native RAM speeds. Okay. Okay, I don't have many conclusions. I have lots of open questions. So how does caching work for data center workloads? What's the data distribution, prefetching, and placement and movement that you can do? You know, what are near data processing capabilities that we could do? You know, some other questions. How do we modify OS, or do we need hypervisor support, user space, all these questions? So this is our goal, to research all these questions using Argo as a platform, and we believe that it's an excellent platform to experiment. So it's time to reconsider coherent distributed shared memory, and it can open lots of new directions. And you can find the software. It's open source. You can download it from this website. Thank you.
And Stefanos also has the same 5-for-1 offer. So
yeah,
you know, you put in 20% time of an engineer, and you will get 100% time back in the same kind of approach. Do we have questions for Stefanos? Jakob.
An obvious question is the economics, right? I mean, think about it. If I need X amount of RAM, I can either buy one fat server just fill it with RAM. I mean, it's easy to buy an Intel server. I mean, simple quad socket gives you 6 terabytes of RAM slots, right?
Right.
It's really easy to fill up on RAM.
Mm-hmm.
The question then becomes, when it's actually cheaper to add more complete computers with a certain size local memory rather than just pouring all your memory into
Right, right. So
that seems to be the value proposition.
obvious question, right? So our department, if we say, okay, let's buy 100 machines or one machine with lots of memory, what do you think they would buy? Not all workloads are big memory workloads. You might have 1 out of 100, but you still want 100 machines for other people to run other software. When it comes time to use this program that doesn't fit anywhere, you have the cluster, easy. And if the cluster is as fast as local memory, then the economics become really good.
It's more about flexibility, the fact that you can have a certain number of cores, a decent amount of memory.
Data centers are just huge, humongous clusters,
Yeah,
right?
The question is really, what's the economics? Because obviously, to buy a bunch of regular 4-core dirt sheet machines, which might scale to 32 gigs, say, or if you buy a true big iron Z
Right. We provide a solution that's software only. We believe that we can bring it close to native speed with prefetching, right? So you will need to do a lot more than just RDMAing across the network. But we believe with right prefetching, decoupled access execute, techniques like that, we can bring it real close to native RAM performance.
More questions? Yep.
So I was thinking about your handling of you're starting to send your software write buffer, I think you called it. You're starting to send when you write to remote data, you start to send the writes to the host node.
Correct.
How do you implement that? Do you trap in the virtual memory, or how do you know that? Or are you having a special compiler that?
No, it's just so everything works in pages. The write buffer is, I don't know, 32, 128 pages. If you try to allocate a new one, you will have to empty one. So it empties as it fills up. But on synchronization, you only have to empty up a fixed amount of pages. It's not going to be gigabytes and gigabytes that you need to write back.
Okay, we have to take the rest of the questions offline for Stefanos. Thank you so much.